My intention is to give you a general overview about the computational models, and especially for those that can be applied from a regulatory point of view. And after that, we try to show you our computational tool, ProtoPRED, that has been developed by ProtoCursor for in silico prediction under REACH and ACH normatives. Sorry, I have lost my mouse. Okay. In silico modeling in silico methods are applied to predict properties. It includes physicochemical properties, toxicological properties, as Hannah has commented, and we usually use expert system and machine learning methods, but other methods can be used. All these in silico methods can be applied for a lot of finalities, as prediction of molecular properties, understanding mechanisms of action, or optimization of molecules. I will focus in the first part, the prediction of molecular properties. That can be ecotoxicological properties, toxicological properties, physicochemical, also ADME properties that are focused in absorption, distribution, metabolism, and excretion of drugs, of chemicals, and also to predict bioactivities. As many of you know, REACH normative, when you register a new substance, require that you provide a lot of endpoints that characterize your molecule. For instance, you have here an example of the endpoints that are required when you register more than 1 ton of a molecule that are stated in Annex 7 of REACH normative. When you increase the quantity of your substance, you have to include more endpoints. You have here also an example, but also the endpoints stated by Annex 7. And it increases, this list increases when you increase the quantity of a molecule to be registered in Annex 9 and in Annex 10. At the end, you have to report a lot of properties of your molecule, and it implies a lot of inversion in resources, in time, and also involves sometimes, as the in vivo assays, that implies animal experimentation. This normative states that registrants must use existing information and non-test methods in order to meet these information requirements, and the testing invertebrates must be only used at last resort. In order to avoid this testing invertebrate animals, the alternative methods to animal testing that are recommended by REACH are these 4. The weight of evidence approach that involves collecting all the data available about my molecule, including precursors and also moleculars that are the result of the biodegradation, analogs, and every information that you can collect. They also suggest in vitro and in chemical methods, and finally the computational methods that you have here stated, and we will go after that in following slides more in detail, but are train analysis and read across, and in other categories you can find the quantitative and non-quantitative structure-activity relationship models. From other part, ICH-M7 normative, that as a method is focused in the prediction or in the establishment of the mutageneity of impurities, allows you to classify in class 1, 2, and 5 if you have experimental data available, but if you don't have this data, either for in vivo or in vitro assays, they recommend you to use in silico methods. These in silico methods will allow you to classify in class 3, class 4, and class 5 depending on the result. If you have at the end no conclusive results, you will require further expert assessment. These computational methods recommended or stated by this normative are 2. From one side, the SAR, that is the rule-based approach, and from other side, the Cursor approach, that is a statistical method. Depending on the common result of these 2 methods, you will classify as positive, negative, or uncertain. Moreover, this normative also needs to characterize my molecule in the court of concern. They are substructures that are classified to be very to have a very risk in carcinogenicity, that are aflatoxins, nitrosamines, and also toxic compounds. By different mechanisms, they present very high risk for our health. Sorry. So I'm going to present the different in silico approaches that you can use from the regulatory point of view, but I need to introduce you little concepts. The first concept is what are an analog chemical. An analog chemical to other means that these molecules share either similar characteristics, structural or functional, or they are classified inside an equivalent chemical profile. As a very brief example, here you have morphine and heroin. They are structural analogs because they have a very similar structure, chemical structure. But in other side, you can see the fentanyl that despite not being similar structurally, it is a functional analog because they behave in the same way. The other concept important to understand these molecular methods, these computational methods, are the molecular descriptors. A molecular descriptor is a property or characteristic that describes a molecule. It means that it can be the number of atoms or other structural characteristic. It can be a physicochemical property, three-dimensional characteristic, or very complex descriptors. As an example, it is just too easy to understand. Here I can characterize or I can extract several features, as can be the number of nitrogens, the number of benzene groups. I also can calculate the lockout, the partition coefficient, as a script. Taking this into account, I will introduce the 4 types that ProtoREACH recommends for registration. The first one is read across. It consists in the inference of a value of a property of interest for an analog molecule. What does it mean? If you see this graph, you can see if you put together analogs for my molecule, you can see that they can form a cluster here that behaves similarly. It means has similar value for the descriptor and they have similar value for the property. If, for instance, my molecule of interest I want to predict is here, has this value of the analog, you can infer the value of the property from the analogs of my molecule. Another approach that is similar, is based on the same principle, is to establish a linear relationship between the descriptor value. I cannot see my mouse all the time. Okay. Between the descriptor value and the property value. So I can establish a trend line, and if my descriptor has this value, I just extract the value of the property from here. In the other category, you can find the structure-activity relationships. The first one is not quantitative, so it's just a classification of a substance by the presence of absence or absence of substructures related with a property. For instance, you can see here depicted, this is an alert that is directly related with mutagenicity. And for the other part, we have the quantitative structure-activity relationship models that are complex mathematical models between the descriptors and the property of interest. It usually uses more than one descriptors. It's not like in the case of trend analysis. It's not based on analogs and are very complex mathematical models that can be tree-based, multilinear regression, etc. I'm going to deep into the Cursor models because they are very complex and sometimes they are difficult to understand. So here you can see a general Cursor model workflow for the generation of Cursor models. We collect an initial raw data set from public databases or literature. When we collect structures, very well-defined structures, and a property of interest as can be, for instance, solubility. After data curation, this is the first step to clean these incorrect molecules, I calculate the descriptors. We calculate a very high number of descriptors that describe every of the molecules of my data sets. After that, the data set is split, and these two sets are the training set. It will be used to select to select the relevant descriptors and to develop the model. And the validation set is pulled apart, and the model doesn't see this validation set as its only user for model validation. I will go into slides with this more in detail, but this is a general overview. If you have any doubt, you can ask us by the chat or by mail or whatever. So when we develop a model for regulatory validity, we have to follow the OECD principles for cursor models. The first one is to have well-defined endpoint. It means that I have to state when I develop the model what is the measure or the experimental value I want to model. It means I have to specify the source of the data, the units of the data, it has to be homogeneous, and I have to specify. The second one implies an unambiguous algorithm. It means that all deep learning is discarded by principle. The third approach is that I have to define an applicability domain of my model. It means the chemical space where I can apply my model. I have not applied this model outside of this applicability domain. The principle 4 that I think is the most important to mention today is the appropriate performance measures. And the principle 5, the last one, is, if possible, a mechanistic interpretation of my model. This is the most difficult part, and sometimes it's not possible, and the normative knows that and states that. So going back to the principle 4, I want to mention how can I measure the performance of my model. So here you have that when I develop a model, it can be a classification model, that is qualitative model, for instance, toxic, not toxic, is binary classification, or I can make a regression model that is quantitative, for instance, the day of the gradations, that is a continuous value. In the classification, in order to measure how this model is able to predict, I construct the confusion matrix, that is the matrix that you can see here, when in the diagonal I see the correct predicted values for negative and positive values, and the inverse diagonal are the non-well predicted values, either for negative or for positive. Sorry, but my mouse is out. With these values of this confusion matrix, I can extract 3 main statistical values in order to measure how this model is behaving. The first one is the accuracy, that measures all the correct molecules, all the correctly predicted molecules in negative and positive. The sensitivity or true positive ratio, is how the model is able to predict positive molecules, and specificity measures how the model is able to predict negative values. From other part, in regression models, we always compare the same way predicted values with observed values, and I can establish a trend line or the correlation line in order to see if they behave in the same way or they are totally different. A slide more, just to go a little into classification models. From this matrix, here you have an example of a confusion matrix from training set and validation set from a model. Here you can see if we calculate all the statistical parameters I mentioned before, you can see that we are able to predict correctly the 92.5% of the molecules in a training set. These measures, or these parameters, are a measure of the robustness of the model because it is predicted on the training set. When I apply the model for a validation set, remember that the model doesn't know nothing about this data. You have different measures, of course, but it is a measure of predictivity. In that case, I am able to predict, I only fail in one molecule for 4 molecules that are correctly predicted, as you can see here in general view of accuracy for all positive and negative. When I, moreover, following the OECD guidelines for cursor models, I should report all the information about my models, and it is performed by 2 documents. The first one is the cursor model reporting format, or QMRF, that has all the information about the Qsar model, about the source, about the type, the development, the descriptors, the applicability domain, etc. Following always the OECD principles. The second document is the Qsar prediction reporting format, the ProtoREACH, that is also an harmonized template that is the result of you have to provide information about sorry, the application of my model on a specific substance. Me voy a ahogar. All this information in both reports is structured according to the OECD principles in the validation of Qsar models in order to ensure the transparency, the consistency, and the acceptability of the Qsar models. And here you have the link about the information from the ECA about the construction and development of Qsar models. So we have from ProtoQsar developed an online platform for prediction of chemical properties of Qsar models, and with your permission I'm going to present the platform. Sorry, I have to change. Thank you. Thank you. So here I think, okay, you can see the platform. So it has been developed modularly. It has different modules aimed or focused in different finalities. The first one is ProtoICH, that is focused in mutagenicity prediction of impurities. ProtoREACH, that is focused in risk-related endpoints and also facilitates to select one annex. The endpoints that are required by one annex, you will see after that. ProtoADME, that is focused on the prediction of ADME properties. And also we have ProtoPHISCEM, ProtoTOX, and ProtoECHO that are compile different endpoints depending on the nature of the endpoints, of the properties to predict. The first one is for physicochemical properties, ProtoTOX for toxicological properties, and ProtoECHO for ecotoxicological properties. If you go, for instance, inside a module, you will see a general description. Here, in the medium part of the web, you can see different links. It will go, I think it can be seen, okay. You will go for a brochure when you have general information about the model, the endpoint, and also all the metrics regarding the performance of the model. Sorry, okay, I'll be back. This is for all the models that you want to consult. If you have any doubt, you can ask us, no problem. In the lower part, you will have 3 buttons. The first one is if you want any information, quotation, whatever, you can link. It is a contact form. In the second one, this is also a contact form that will provide you a trial access when you can try all the platform with a limited number of molecules. And in the last one, if you have credentials, you can access the platform. With your permission, I will begin with ProtoREACH, and after that, I will come back to ProtoICH. Here you also have the list of endpoints that we have. I will go one side, and it is just to show you how does it work. You can see in the upper part, this is the part to input molecules. You can load a file with the formats that are stated here. If you have any doubt about how to construct the files for here, you can go to About section. I will move very quickly to show you. In About section, you can see an example for every input file that you need. Okay. I can also draw a molecule, whichever you need. After that, you have to get the smiles because the platform works on smiles, so I get the smiles. I can also edit, so I will get again, okay? I can directly write the smiles, and I can edit the molecule afterwards. Do not forget to get the smiles again. You can also work by your Cas number. I don't remember, this is, oh, I can use, sorry, dyslexic part of my life. It will retrieve the Cas. If this is not present, because it gets the smiles from open servers for public databases, if you don't have the Cas number, it will not be retrieved, but you can enter manually the smiles. And also in the lower part, you can add additional information of your molecule. For instance, the Cas number is stated here because you have indicate here, but if I use, for instance, a smile, I can complete this information to be present in the final report. Okay, I will work with, I don't know what molecule. Okay, I will go with that. I have selected a molecule for you. I will introduce, you can see here, I can edit. And in the lower part, you will see the model selection part. In ProtoREACH, it is with different subsections regarding the nature of the properties, physicochemical, toxicological, and ecotoxicological. You can select by section, you can select all, or you can select by annex. This is very useful if you don't know the annex that are needed or that requires these properties. So I just select and they say, and the platform will say you what do you need. For instance, I will go to self-extension. Okay, I have the molecule, I select an endpoint, and okay, it will check. As you can see, it talks about tokens because the platform is paid by tokens. So just 1 second, I will back. The prices of every endpoint is indicated here, depending on the difficulty or the substitution of the experimental results, the experiments that we want to replace. It has different costs. You can see here physicochemical properties are 3 tokens, and on-site toxicological properties, they are 4 tokens if it substitutes an in vitro assay, or 10 tokens if it substitutes an in vivo assay. So after I am agree about the cost of the prediction, I submit. It goes very fast. Nevertheless, it depends on the model and on the complexity of my molecule, but in any case, it goes very fast. And I obtain always the result as a table, HTML format. It indicates the experimental value. If it is present in our database, it will be here. Also the predicted value, and the conclusion about the applicability domain. If it is on-site, outside, and what is the method that has been used to determine it. You can download the result as an Excel file, and you can also generate the reports. The QPREF, that is the application of the model into my model. If you go here, you can change your user information. It will use the number of the user, but you can change it how you want. You can also add additional comments. For instance, if you want to conclude, if you have any information, additional information that you want to state about the behavior, about other weight of evidence that you have, about other identifiers, whatever. And after that, I can generate the QPREF. Okay, it is downloaded, I think you can see here, as a zip form. Okay. And here you have your QPREF dossier of our model applied to your molecule. As I stated before, it is structured following the guidelines of the OECD, indicating all the information about the substance, all the information about the QPREF, the prediction about the endpoint, following again the principles stated by the guidelines, what descriptor has been used, etc., all the principles. At the end, we have included some information about the performance of the model, the adequacy of the model, and I think that most important is to highlight this part. Here you have the conclusion of your molecule and what the normative says you about the different results that you can have. We always try to put some hints about the interpretation of the results. Here if you have any additional information, you can see here. You can comment everything you want, and at the end also we include structural analogs that are present in our dataset. It serves as a help for toxicological expert toxicologists in order to interpret the results, in order to interpret how the model works for analogs, and you can see this is especially useful for them, but it makes you, gives you hints about the results. Okay, here? It's okay? Perfect. Sorry, but I forgot to mention one thing more. When I'm here selecting my endpoints, I can download at any time the QMRF. For instance, I will back to self-extension, that was the endpoint that we were working on. Okay, so here again you can see all the information required by OECD guidelines, including the authors, including the company, the developers, and all the principles required. Here you can find a lot of information about the endpoint, following the first principle, how this data has been collected, has been processed, and what does this data means. You can see here in the first principle, and every information that needs to be clarified, you can ask if you have any doubt. No problem. We are very welcome to help you. Okay. In the upper part, when you make prediction, these tokens or the remaining tokens are always present here, and also you can access your profile by your username here, and here you have a list of your historic movements. If you have any doubt about previous predictions, you can just to see here and to be sure that everything is correct. With your permission, I will move to ProtoICH module. Here we have implemented the the two models that are required by normative, that is the statistical method and the expert rule-based method, but also we have implemented the court of concern profiler that is compulsory from the last year, in fact. Again, the input molecule section is the same in every module, so you can write, you can draw, you can input the cast number. I will use another molecule with your permission. Okay, this is my new molecule, and in that case, as it is all together as a module, you only can have the option to perform the 3 analyses at the same time. Again, you can see here the different documentation, the QMRF for these models. I check input data. Okay, I have token enough, so I have to submit. It takes a little because I have 3 models and not one only. Okay. The information of the result is the same. By model, you will have the experimental value if it is accessible, the predicted value. In that case, we also indicate the reliability of the prediction, and if the molecule is inside or outside applicability domain. For the expert rule-based model, you have here a summary of the alerts detected, and also the carcinogenicity court of concern profiler or identifier. You also see if they have any alerts. In the same way, you can use this part to perform custom QPREFs and get the reports. Again, it takes a little more than one single prediction. Okay. In that case, we will provide the prediction performed by the spread root model, the prediction performed by the Cursor model, and also we provide a consensus report that is a summary for all the three predictions. In that case, it is structured in different sections. I will show you very briefly. The first part is always the identification of the substance. Here you have the results for the Cursor model. This is very briefly summary. The results for the rules-based model with the alerts detected. The cohort of consent profiler also with the alerts and the conclusion. And at the end, there is a consensus or a summary table that has all the information that we have predicted and a conclusion. As before, we try to guide you in the decision for a regulatory point of view. So if it has been classified as mutagenic, we try to explain you what to do with that. Okay, I have this. I think that from my side it's okay. Do you want to say something more about the platform? No?
Let's go. Yes.
Okay, so we will come back. 1 second, Lauri. No.
Okay, so thank you, Eva, for this nice presentation. It was quite nice. And also coming back here, thank you also to being with us until now. I hope you are enjoying. Now I will be quite brief to conclude our webinar. I only would like to highlight a little bit the advantage of using our ProtoPRED platform. I would like to mention and highlight that our platform is useful for many molecules and structures. Since first we have developed our models using large databases, but also we have implemented several methods to evaluate applicability domains. Then also it's a quite clear platform. We have one validated model for each endpoint, which will allow you obtain a really clear model, so to have clear model options, but also clear results. Also, it's a really reliable tool. We have built our models, as I say, my colleagues, following best practices also for the curation of the data, but at the time also to ensure the reliability of the model, the predictiveness, and so on. So to ensure you to have the best possible results. In another hand, it's a quite user-friendly tool where you can get ready to find model descriptions and results, but not only any kind of results. We are also providing these results in the QMRF and QPRF formats, which will ensure you regulatory acceptance. Finally, we have a really good track record because our model have been successful used in several countries in front of bodies regulating different rules, as we mentioned before, REACH and ICH, for example. So, without more, I thank you for your attention. Please, if you are interested in our tools or do you have any specific doubt or you want to receive training, please feel free to contact us through our website or the emails we are providing here. Thank you.
Okay, now we have seen in the chat some questions. I will move. Can I?
Okay, fine, we are back. So we have received a question from Margarita Bulatova, who is asking us if can training validation be done in several iterations to make the model even more precise?
Okay. So to answer your question, I will go directly to the QMRF. For instance, I will get the causal model for mutagenicity that we have. In that case, in order to have, it is for Margarita, okay. We give you parameters, as I said before, for the application of the causal model into the training set, as it is. We also give you statistics about the cross-validation, but I guess that is what you mentioned, is the cross-validation. So we apply the model for the training and test set inside the training set. We also give this external validation results, and at the end we give this is validation, this is inside the validation. We give all the metrics to apply the model by cross-validation in training and validation set. So we try to measure in every using every method that we can to measure our validity. We also use, in some cases, for instance, in that case, the scramble metrics. As you know, this consists in make a randomization of the value, the experimental value, and see if the model is working as intended. And we see that it loses totally the precision, so meaning that the model is working well and not by chance. I don't know if I asked correctly your question, Margarita.
Yes.
I can see the questions here. Really? Okay. Okay.
So, reading here, we have another question from Ricard Mola, who is asking us, ICH-M7 established that QSAR predictions must be evaluated in an expert report. Can your company provide this expert report?
Yeah. In fact, this is another question from the same person. Do you have experience in the acceptance by regulatory authorities of the QSAR prediction with ProtoICH? Effectively, we have some reports, some companies that have requested prediction for mutagenicity prediction of impurities. And we also collaborate with European Registered Toxicologists, that is the person who performed this expert report. So she uses our tool to predict, to perform the QSAR, the cohort of concern, and the SAR model, and with that and her expertise, it performs the final expert report, and they have been submitted successfully for authorities. Thank you, Ricard, for your question. In fact.
Okay, so I think we have another question from Judith Vigas. Thanks to you, Judith, to be here today with us. So she's saying, it's a question regarding QSAR model. What are the main limitations of QSAR models? Are there some kind of molecules that cannot be well predicted?
Yeah, the limitation is regarding the atoms. So if they are focused only on organic molecules, it means that they can include carbon, oxygen, sulfur, phosphorus. So inorganic molecules are not well predicted and are totally outside of the applicability domain. In fact, they are not allowed by the platform. We cannot predict directly mixtures. We can manage and make prediction of mixtures as a service, but not by the platform. And complex molecules, it means that it's not. This is only for discrete organic molecules.
Okay, I think we don't have any other questions. Anyway, you can feel free to contact us wherever you want. You can go through our website, you can contact us directly, but also we will leave all this material, the recording of the webinar will be available at our YouTube channel, so please feel free. We remain to your disposal. Thank you a lot for your time and to be with us today.
Thank you very much. Thank you for being here. Thank you, Anna. Have a nice day.
Bye.